In this video, I'm going to go through the OCR A-level chemistry paper. This is the 2020 paper, paper 1, periodic table, elements and physical chemistry. I'll just do the first half of the paper in this video. Okay, so starting off with the multiple choice section. Okay, several students titrate 25 centimeters cubed of sodium hydroxide with hydrochloric acid. Okay, so they pipetted the sodium hydroxide into the conical flask, and so just so we have got our NaOH in there, and here we're putting the hydrochloric acid in. One student gets a smaller titer than the others. What could explain the smaller titer? The burette readings are taken from the top of the meniscus instead of the bottom. That shouldn't make any difference, because if he takes it from the top for the initial reading and the final reading, that should be okay. The conical flask is rinsed with water before carrying it. That won't affect it because you're not changing the moles of NaOH. You just got a bit of water in there. An air bubble is released from the jet of the burette. Now that would actually make the titer bigger, because you would be measuring the volume of that bubble, and you don't need to add in addition to the volume of the liquid. So it's got to be this one. And the pipette is rinsed with water before filling with NaOH. Yeah, that would do it. The pipette should be rinsed with the solution you use, the NaOH. Yeah, if you rinse it with water, you're going to dilute the NaOH, and then you'll need less acid. So the answer is D. Okay, which statement gives the numerical value of the Avogadro constant, which is of course about 6 times 10 to the 23. The number of moles of 12, no, that's wrong, because that's just be 1 mole, won't it? Yeah. The number of molecules in 16 grams of oxygen, well, that would be half a mole of oxygen. That would be because the MR of O2 is 32, because it's O2, yeah. So that would be 0.5 of a mole. So that would be the number of molecules. That would be half of the Avogadro constant. So it's not that one. The number of atoms in 1 mole of chlorine molecules. Sorry, I've just said that wrong, haven't I? Here. 16 grams, sorry, yeah, it would be the, yeah, that is right, what I said. So it's not that one. The number of atoms in 1 mole of chlorine molecules. 1 mole of chlorine molecules, well, that's Cl2. So you'd have 2 moles of chlorine atoms. So that would be double the Avogadro constant. So it's got to be this one. Well, let's work out the moles of calcium. That's equal to mass over the AR, which is about 40, which is 40.1. So that's equal to half a mole of calcium. But when calcium reacts with oxygen, each calcium loses 2 electrons to form the 2+ ions. So it will release the Avogadro constant number of electrons. Okay, so it'll be a half of mole of calcium, but each one releases 2 electrons, so that's a whole mole's worth of electrons, if you like. So B is the answer there. Okay, so 0.8 grams of an element is react with 0.4 grams of oxygen. Okay, so which is the identity? So let's do it this way, I think. Let's do the moles of oxygen atoms. That's going to be 0.4 over 16, which is a 0.025. So therefore, the moles of X we must have, well, it's got to be that multiplied by 1.5, multiplied by 2/3, sorry. Because you've got 3 options for every 2 X's. So that gives you 0.0167 moles of X. What's the mass of X? It's 0.8 grams. So the atomic AR is going to be equal to the mass over the number of moles. The mass is 0.8. over 0.0167. That gives you 48. Check in your periodic table which element has an AR of 48. It is titanium is the closest one. So quite a lot of work there for your mark. Okay. Okay. Phosphoric acid, right? So phosphoric acid is a tribasic acid. That means there's 3 hydrogens there, so it's H3PO4, right? And it's going to react with calcium hydroxide. So the formula of the calcium phosphate is going to be, because that's a 3- ion, and calcium is a 2+ ion, it's going to be Ca3PO4 2. So they're going to react in the ratio of 2 to 3. Okay, so how many moles of phosphoric acid have we got there? Concentration times volume, 0.1 times 0.1 is equal to 0.01 moles. So how many moles of calcium hydroxide then? Well, it's going to be 3 over 2 times that, isn't it? We've got 3 there, 2 there. So moles of calcium hydroxide, 0.01 times 3 over 2 is equal to 0.015. Okay, now we need to work out the mass of calcium hydroxide. All right, so mass is equal to moles times MR. The MR of calcium hydroxide is 74.1. Okay, so the mass of calcium hydroxide, moles times MR, 0.015 multiplied by 74.1 gives us 1.11 grams. So C is the answer there. Okay, which statement, number 5, which statement about elements in the D block is correct? Right. Chromium, right. Chromium, if you just write the elements out, so we've got potassium, period 4, potassium, calcium, scandium, titanium, vanadium, chromium. Okay, so you might expect, right, calcium is 4s1, sorry, potassium 4s1, calcium 4s2, and scandium is going to be 3d1, titanium 3d2, vanadium 3d3. You might expect chromium to be 3d4, but of course it's not. It's 3d5 and 4s1. It kind of borrows one from the 4s. So that is correct. Right, so the rest should all be wrong. Copper 1+ ions contain an incomplete D subshell. Well, that's wrong because the electronic structure of copper is 3d10 4s1. So in the copper 1+ ion, you lose the s electron. You've got a full D shell. Yep. Fe2+ contains 3 unpaired electrons. Well, Fe is the next one after chromium. So Fe is actually, electronic structure is 3d, so it's manganese after chromium, then iron. So iron is 3d6 4s2, right? So the Fe2+ ion is 3d6, right? Those, of course, are going to be, you've got 5 d shells like that. So you're going to have just one of the orbitals has got a paired, okay? So it doesn't contain 3 unpaired, it contains 4 unpaired electrons, as you can see there. Scandium forms ions with different oxidation states, which doesn't. Scandium has only got 1 electron in its 3d shell, and it always loses all of those electrons to form the scandium 3+ ion. It only ever forms a +3 oxidation state. So A is the correct answer there. Right. an enthalpy one here. Right. Now, if you kind of aware, you probably, without doing a calculation, you probably can tell what the answer to this one is, right? The equation for the combustion of C7H8, okay, heptane, shown by that equation. Calculate the enthalpy change of combustion for the hydrocarbon. Well, first of all, it can't possibly be C or D because they are positive, they're endothermic. Burning things is never endothermic. So it's going to be either A or B, and you probably know that for methane, okay, delta H combustion of methane is equal to minus 890 kilojoules per mole. So it can't, B is way too small, it's got to be A. But let's do the calculation because you shouldn't really guess like that, I suppose. Right, so how are we going to do that? Well, we're given delta HF value. So I'm going to draw a Hess's law triangle. And the third thing I'm going to put down in the Hess's law triangle are the elements in the standard states. So 7 carbons, and we're going to have 4 H2s. Okay. Put that one in a different color. Right, so the red arrow, all we're doing is we're burning the C7H8. So that's going to have a value of, so we're not burning, forming 1 mole of that. So that's going to be plus 12 kilojoules per mole. On the blue arrow, we're forming 7 moles of CO2. So that's going to be 7 times 394 for forming carbon dioxide. And we're forming 4 molecules of water. So it's 4 times minus 286. Add that lot up together, you get minus 3,902. Now we want to work out that delta H there, which is done in green, delta H. So we're going against the red arrow, so we turn that plus 12 into a minus 12. We're going to go that way. And then we're staying with the blue arrow. Going up there. So that is going to be, that stays the sign. And that is equal to minus 3914 kilojoules per mole. So A is the answer there. Okay, we've got a Boltzmann curve there. Right, when we have a higher temperature, what happens to the peak? Well, it goes like this. Right, so the peak shifts to the right because the average, the sort of the most probable energy goes higher of the molecules, but the peak is also lower because the area under the curve has got to be the same as the first one. So the peak is lower. So the peak increases in height is wrong. The peak decreases in height and moves to the left, no, it moves to the right. It is that one there, D. It's a fairly standard question on the Boltzmann curve. Okay, right. Graph is plotted of ln K against 1 over T. So this, we're talking about the Arrhenius plot here, okay? And you can use it to find out the activation energy, okay? Now, if you remember, the Arrhenius equation is ln K is equal to minus EA over R, 1 over temperature, plus ln A, which we don't care about as a constant. So we linearize that, y mx plus c. If you plot ln K on the y-axis against 1 over the temperature in Kelvin on the x-axis, we are going to get a gradient equal to minus EA over R. Okay, so M is equal to minus EA over R. We want to find out the EA, activation energy. So it's the minus gradient over R, the gas constant. Okay, so that is going to be minus 55,000. Right, I'll rearrange that incorrectly, silly me. Times R. Okay, that's better. It's going to be minus that, so that's going to become a plus 8.31. Now, what are the units of What are the units of the ideal gas constant? Well, it's in joules per mole per Kelvin. So our activation energy is going to be in joules here, not kilojoules. So if you multiply that out, you get 457,000. Okay, joules. So that's going to be equal to 457 kilojoules. So that is our answer there. Okay. It's important to remember there that the units of the ideal gas constant is joules per mole per Kelvin, not kilojoules. Okay. Right. Number 9. Right. Okay, so we've got nitrogen and hydrogen combining to form ammonia. To give us the partial pressures of nitrogen and the partial pressure of hydrogen and the total pressure. So the first thing we're going to do, we can work out the partial pressure of ammonia by subtracting. So the partial pressure of ammonia is equal to the total pressure, 25 megapascals, minus the partial pressure of nitrogen, 18.75, and the pressure of hydrogen, 2.5. That gives us 3.75 megapascals. Okay, right. We want to work out what Kp is, though. But Kp, all right, is equal to the expression there. We look at this is going to be the partial pressure of ammonia squared divided by the partial pressure of nitrogen multiplied by the partial pressure of hydrogen cubed. Okay, put those numbers in. 3.75 squared over 2.5 cubed for the hydrogen times by 18.75 for the partial pressure of the nitrogen, and that gives us 0.048. And the units are going to be in well, we've got megapascals squared on the top, megapascals for the nitrogen, and megapascals cubed for the hydrogen. So that's equal to, that simplifies to megapascals to the -2. So this B is the answer there. Okay, right. Now, the reaction for the equation of ICl and hydrogen is shown below. And the rate constant for this reaction is that now, and it wants the overall order for the reaction. How the way we're going to work that out is be from the unit of the rate constant. That's how we're going to do that. Okay, so that's the only way we can tell what it is. So if we get, let's say that rate, let's say it's second order overall. Let's just test that. I think it is second order. So here's the concentration, sorry, of everything. I'll just put K, and that's the concentration of the iodine and the hydrogen. That's going to be cubed. Sorry, squared if it's second order overall. So that means K is equal to rate over the concentration squared. Rate always has units of mole per decimeter cubed per second. Concentration of A is mole per decimeter cubed, but of course that is squared, so that's going to be, one of those will cancel out, so we get second to the -1 over mole per decimeter cubed. Bring that up to the top line, you get second to the -1 mole to the -1 dm to the +3, which is the units we've got there. So it is second order overall. Okay, you can tell the answer from the units there. Okay, right, now this is quite a lot of work for this question here. So we've got hydrochloric acid reacting with sodium hydroxide. Okay, so we're going to have this equation. I would probably do it like this: H plus from the acid, OH minus from the alkali, going to give us H2O, and I would put down here start moles, and before they react, and then final moles and then final concentration. Okay, let's do that. So how many moles of H plus have we got? Well, it's the concentration of the hydrochloric acid, because one hydrochloric acid gives you 1 mole of H plus. So that's conc times volume, which is 0.1 multiplied by 20 over 1,000. That gives you 0.02. 0.002. The concentration of the sodium hydroxide, well, that's going to be here. It's going to be moles. Conc times volume. So concentration 0.1 multiplied by 10 over 1,000 this time, 0.001. Okay, so we can see that the acid is in excess there. We don't really care about the water. Now, all of the OH minus is going to go. It's all going to react. So we're going to have, well, we're going to have a tiny bit less because you always have some, of course. You always have, even in acid, you have a tiny amount of OH minus ions, but we'll approximate it to 0. So how much H plus have we got left? It's going to be, they react in a 1-to-1 ratio. So it's 0.02 minus 0.001 equal to 0.001. Right, now the final concentration of that is going to be over the moles over the volume. Well, what's the volume? We've got 20 centimeters cubed there and 10 there. So the total volume is 30 centimeters cubed. So that's 0.01 divided by the volume, which is 30 centimeters cubed, 30 over 1,000. Evaluate that, and you get 0.033. So that's the hydrogen ion concentration. How do you find the pH from that? Take the minus log. Minus log 0.033 is equal to 1.48. So our answer is D. Again, quite a lot of work to do for 1 mark. Okay, we've got iodide reacting with manganate there. The unbalanced equation is shown below. What's the ratio of MnO2 to OH minus? Right. So what I would probably do here is I'm going to use oxidation numbers first of all. So we've got a +7 is the oxidation number of manganate there, going to +4 there. So that has gone down by 3. That has gained 3 electrons. Whereas the iodide, right, has gone, let's see, the iodide, so minus 1 oxidation state of iodine there, and +5 here. So the iodine has gone up by 4 electrons. It is actually lost 4 electrons. All right, how do we balance that then? We've got to put a 3 in front of the iodine. Okay, we could times the iodine by 3 to give us 12 electrons, and multiply the manganate by 4 to give us 12 electrons. Okay, we've got that there. Now, we just need to balance the other stuff. Okay, so let's have a look here. So that's 3. Okay, it's 4. Oh, sorry, that's 6 electrons. What am I talking about there? Let's start that one again. Sorry. The iodine is going from -1 to +5. That's lost 6 electrons. Whereas the manganate is only gaining 4 electrons. So we can balance. So we multiply the iodine by 2. and the manganate by, let me think, so the iodine by 2 to make it 12 electrons, 2 there, and we multiply the manganate by 3 to give us 12 electrons as well, so 3 manganates goes to 3 MnO2. Right, and now I think we put a 3. Now, we do it, I'll tell you what, we put a 2 there. I'm going to put a 3 here. And 3 iodides, only 2 manganese dioxides, and 1 water, and I will get 2 OH minus there. Okay, so that means the ratio of Mn2 to OH minus, well, it's 2 to 2, so it's 1 to 1. C is the answer there. Okay. Okay, going towards the end of the multiple choice, now number 13. Which statements are correct when a catalyst is added to a dynamic equilibrium? Okay, right. The rates of the forward reaction increase by the same amount. That is true. The concentration of the products and reactions do not change. That's true because it's already at equilibrium, so it won't change the position of equilibrium. And the value of Kc is not affected by a catalyst, of course, because only temperature affects Kc, so it's 1 and 2. So B is the answer there. Okay, which statements for group 2 elements are correct? Okay, right. The second ionization energy of magnesium is greater than the second of calcium. That is true because whenever you go down the group, any group, doesn't matter what group it is, the ionizations first ionization energy goes smaller and the second ionization energy will go smaller because you're getting more shielding. Okay, so that is true. A strontium ion contains a total of 6 electrons in s orbitals. Okay, so there's strontium is 5s. All right, strontium ion, well, we'll lose those 2, of course, but it's got electrons in 1s, 2s, 3s, and 4s. So it's got 8 electrons. So that is wrong. And the equation for the reaction of barium with water, well, this is wrong because of course barium hydroxide. Barium forms a 2+ ion as they all do, so it's going to be BaH twice. So it's only 1 that is correct. So it's D. Right, 15, I think is the last question in the multiple choice. Okay, yeah. All right, let's have a look at this then. Right, which statements of the complex ion? So this is a bidentate ligand, the diaminoethane. Okay, so you only need 3 of them to form 6 coordinate bonds, so which are correct. Right, so well, first of all, it's got 6-4 coordination. Yeah, it does. Okay, and you can see from this diagram here, it does. This is one of the strange things about whenever you have bidentate ligands with this coordination of 6, you get optical isomers. There's 2 possibilities. I've just drawn the diaminoethane as that just to show the ends. Yeah, you can see. So each one forms 2 coordinate bonds, and this one on the on the left is the mirror image, non-superimposable mirror image of the one on the right. So they are optical isomers. So that is correct. Now you can't get cis trans isomers. That's not possible. You get cis trans isomers, just to illustrate, when you have things like 2 chlorine ligands and 4 water ligands. And I've drawn there the chlorines are opposite each other, so that would be called a trans. But if we swap them about, that is now changed it. That's the cis isomer. Okay. Right. Right. Magnesium then. Okay. Question about magnesium, bromine, and magnesium bromide. Right. Relative atomic mass is defined as the weighted mean mass compared with 1/12 of the mass of carbon 12. What's by the weighted mean mass? Well, that is the average mass, taking into account the abundances of the different isotopes. That's all there is to that. Draw a dot cross diagram for magnesium bromide and draw the outer shells only. Okay, so magnesium, right, is going to lose. Magnesium has got 2 electrons in its outer shell, so it's going to lose both of those to form the Mg2+ ion. So that is going to be just like that, no electrons. Bromine, well, it's got 7 electrons in its outer shell. So there's 7 of its own electrons. And then there's the red one, which has got from magnesium. Okay, and you need to say there's 2 of those. And the charge on that is going to be a minus. So it's a fairly straightforward question. Right. Calculate the number of ions in 1.74 grams of magnesium bromide. Okay, so let's work out the moles of magnesium bromide first of all. So the moles, MgBr2, is equal to the mass over the MR. So we've got 1.74. Now the MR of magnesium bromide, magnesium 24.3 and bromine 79.9, so that's 184.1. That's equal to 9.45 times 10 to the minus 3 moles. Right, now how many moles of ions have we got in 1 mole of that? Well, we've got 1 mole of magnesium ion and 2 moles of bromide ion. So we've got 3 moles of ions in 1 mole of substance. So the moles of ions, 9.45 times 10 to the minus 3 multiplied by 3, which gives us 0.02835. We want the number of ions, so we've got the number of moles, so we need to multiply our moles by the Avogadro constant. Okay, so the Avogadro constant is 6.023 times 10 to the 23. So the number of ions is equal to that multiplied by the Avogadro constant, and that gives us 1.71 times 10 to the 22 ions. Okay, and that's the, oh, actually, well, if you work it out, it's 1.7077 times 10 to the 22. So to 3 sig figs, that's 1.71 times 10 to the 22. Right. Now it is a 6 marker question on talking about the structure of bonding and physical properties. What can we say here for 6 marks? I think you need to mention, let's start off with magnesium. Well, you need to say definitely it's metallic bonding, isn't it? Probably say what metallic bonding is. It's a load of magnesium 2+ ions in a sea of delocalized electrons. What is metallic bonding? It's the attraction of the positive ions for the negative electrons. That's strong, so that's why it's got a high melting point. always worthwhile saying you need a lot of energy to overcome it. Quite often in mark schemes it says that, the energy thing, people forget to mention it. Right, is it a conductor, magnesium? Yes, it is a conductor when it is solid and liquid because it's got delocalized electrons. They carry the charge. Okay, let's now do bromine. Well, what we're going to say about bromine, they are small molecules, small covalent molecules. So what's holding them together are weak London forces, because there's no permanent dipole in the bromine molecule. So they're pretty weak, so that's why it's got a low boiling point. It's got no ions and it's got no delocalized electrons, so it won't conduct electricity. Worthwhile mentioning that. Finally, magnesium bromide. Well, it's an ionic lattice, isn't it? I say strong electrostatic attractions. Between the Mg2 plus ions and the Br minus ions, and it will conduct electricity, not when it's solid, because there's when it is molten, because the ions can move when it's molten, and there's a flow of charge. That's what electric current is, and it flow of charge. So that's what will conduct electricity. Okay. Now we have a question on the Bourne-Haber cycle. All right. Incomplete Bourne-Haber cycle. Right. And we've got the data on the right-hand side, which we're going to use in the next part. Right, for 2 marks on the dotted lines, add the species present, including the state symbols. Okay, so here, this one here, look, we form magnesium bromide. Right, must be the elements in the standard state, so that's going to be magnesium solid, and the standard state of bromine is Br2 liquid. So liquid, yeah. And so what we do in that first step, we're atomizing the bromine, and we're atomizing the magnesium in that step. First ionization energy, the magnesium here. Magnesium forms a 2 plus ion, so this other step, this must be the second ionization energy. So we're going to have Mg2 plus gas plus 2Br minus gas. Sorry, 2Br, not Br minus yet, because we haven't stuck the electrons on them. Plus 2 electrons. Okay, and that's everything there. That's our 2 marks. Now the next part of the question, it says, use your completed energy cycle to calculate the enthalpy change of hydration of bromide ions. Okay, so I'm going to and that's 2 marks there, so we're going to put the numbers in here. Okay, so let's look at this table 16.2 here. The first ionization energy of magnesium, 736, well, that's that one there. The second ionization energy, well, that's that one there, that's 1450. The atomization of bromine, well, here we atomize bromine, this step here, but we've got to be careful because we form 2 moles of bromine, so it's 2 times 112, which is equal to 224. Okay, so I'll just rub that out, make it clearer. This arrow going down, that's the enthalpy of formation of magnesium bromide, which enthalpy of formation of magnesium bromide minus 525. So I'm going to not worry about the signs because the arrow is going down. We know it's minus anyway. Then this bottom arrow, what we're doing there, we are dissolving magnesium bromide. So that's the heat of solution of magnesium bromide. That's minus 186. Okay, right, now we need to fill it in. Oh, here, what we're doing for this one missing is we're atomizing magnesium. That's 148 there. That one there, we are sticking on electrons onto bromine. That's 2 times the electron affinity. of bromine. That's 2 times 325. And that's minus again, that's equal to minus 650. Here, all we are doing is we are, this one, magnesium ions gas and magnesium aqueous, so that's a hydration of magnesium ions. That is minus 1926. And then this bottom one, all we're doing there is we are hydrating 2 moles of bromide ions. Okay, so let's call that X. Let's call that 2x. Okay, now we're going to add up everything on this side. Add up all that lot. Don't worry about the signs because we can see that the arrows are going. You just make everything positive, and we get a value there of 3269. Let's add up everything here in blue. That bit there that adds up to 2526, 2576. Don't worry about the sign. Now, so we want to find this difference 2x here. So 2x is going to be equal to 3269 minus, and not worry about the signs again, 2576, which gives us 693. So x is equal to half of 693. That's 346.5. Okay, that is the hydration of the bromide ion, kilojoules per mole. There's our answer there. Right. Well, we have to before we do that, we have to say what sign is it? Well, the arrow is going down here, so that means it's exothermic, so we must put a minus sign in there. Nearly forgot that. So the value is minus 346.5 kilojoules per mole. Okay. Now, the next bit of this question is tricky. Okay, let's do that. Well, first of all, it says write the equation for the lattice enthalpy of magnesium bromide. So I think it wants lattice enthalpy of formation, and then it says calculate the lattice enthalpy for 3 marks. So let's write the lattice enthalpy formation is you've got Mg2 plus ions in the gaseous state, really important to the state symbols, and 2 moles of bromide ions, again in the gaseous state, and that is going to give us magnesium bromide solid. Okay, that is the equation there. Now, how are we going to do that calculation? We've got to bear in mind that. So we want to go from, I'm going to rub out some of this stuff here so we can see more clearly. Okay. Now, what we've got to do is, let's home in on what we need to do. We need to go from, do it in orange. What is the lattice enthalpy? We've got the gaseous ions up here in orange, and we need to go down to here, the solid. So we need to find out the value of that orange line there. I'm going to rub that blue bit out, make it clearer. How are we going to find out that? Okay, so we've got 1926 there, haven't we? Yeah, for that bit. That bit there is 1926 kilojoules. And then we have got this extra bit for magnesium 2 plus. Right, so how are we going to work that out? Okay, so that's going to be so this bit, right? Well, we know that that bit there, yeah, that bit there, do it in yellow. That is the hydration of the bromide atoms, which was 693. But we need to subtract from it this little green bit here, don't we? Okay, so that green bit. And what is that green bit? That is the enthalpy of, sorry, not that bit. We need to subtract that green bit there. And that's the enthalpy of solution, which is minus 186. Okay, so the lattice enthalpy is going to be 1926 plus 693. And then take away that green bit, minus 186. And that is equal to 2,433. And we need to give it a sign. Well, the arrow is going down. That's our orange arrow, yeah, that one there. It's going down, so it's minus. So the answer is minus 2,433 kilojoules per mole. That's quite tricky and quite confusing. Okay. Okay, here we've got methanol being made by the reaction of carbon monoxide with hydrogen. Predict the conditions of pressure and equilibrium that would give maximum equilibrium yield. Okay, so let's have a look here. First of all, it is an exothermic reaction. So equilibrium yield, we should use a low temperature. Le Chatelier tells us that the equilibrium will move to the right, will move in the exo direction, which is right. And what kind of pressure should we use? Well, we've got 3 moles of gas on the left-hand side and only 1 on the right. So we should use a high pressure, because that will move the equilibrium to the side with the fewest gas moles. Okay, right. Right. A catalyst is used in the production of methanol. State 2 ways in which the catalyst helps reduce chemical companies make their processes more sustainable. Right. Now, I was a little bit flummoxed with this, so I actually looked at the mark scheme. I would say basically, well, catalysts, how do they help? Because you can use a lower temperature. So you need less energy for that. So you get less CO2 emissions, which I would really say was just one reason. But that they actually say that's 2 reasons. They say lower temperature, they can't give you 1 mark for that. And then you gave what the second reason was less energy and less CO2 emissions. But to me, that just seems like one reason. But anyway, that's all you've got all right. Entropy values. Okay, right. So you've got the entropy values. Chemists proposed making the methanol using this equation here, which I've pasted in again. Okay. Explain with a calculation whether the production of methanol is feasible at 525 kelvins. Okay, so what we've got to do there is we have got to, I haven't really left myself much space there, but we know the equation for delta G, which will tell us if a reaction is feasible. Delta G is equal to delta H minus T delta S. Okay, so we are given delta H there. So it's minus 91. Now let's work out the entropy change, delta S. So the entropy change is the products, the entropy of the products minus the reactants. So the product is methanol. So that's going to be 238 minus, right, carbon monoxide is 198 plus 2 times 2 lots of hydrogen. So that's 231, 2 times 131. So that's 238 minus 460. and that gives us a value of minus 222. And very importantly, that is in joules per mole per Kelvin, not in kilojoules, whereas delta H is measured in kilojoules. So we need to convert this value into kilojoules. That is equal to minus 0.22 kilojoules per mole per Kelvin. Right, let's put that into our equation. So we want minus the temperature is 525, and the entropy change is minus 0.22. Okay, so that's minus 91, and that becomes a plus now, doesn't it? That becomes plus 116.5. That makes delta G positive. That makes it plus 25 let's round it up to 6 kilojoules per mole. Importantly, it's positive, and that means the reaction is not feasible. Reactions are not feasible when the delta G value is positive. Okay, so that's quite straightforward for 5 marks, really. Just putting a load of numbers in. Okay. Right, and then we're going to use this relationship here. Delta G is RT minus ln Kp, and we need to calculate Kp. Okay, so we need to rearrange this equation, and we're going to get ln Kp is equal to minus delta G over RT. Right, we have to be careful with our values here. Delta G, they've given it as in joules per mole, and that is good because the ideal gas constant R is given in joules per mole per Kelvin, and that is equal to what is it, 8.314 joule per mole per Kelvin. So ln Kp is equal to, right, minus, so it makes that positive 2.48 times 10 to the 4 over 8.314 multiplied by the temperature, which is 298. That gives us a value of 10.014. Right, that's ln Kp. So ln Kp is equal to that. So do the anti-logs of that. So that means Kp is equal to E to the power of 10.014, which is equal to 2243. Okay, give it to 3 significant figures. So we should give that to 2200. And the units, well, let's write down the expression. Well, we had, so for the equation, we had CO plus 3H2, wasn't it? 2H2 goes to CH3OH. So Kp is going to be equal to the partial pressure of methanol in atmospheres divided by the partial pressure of CO in atmospheres multiplied by the partial pressure of H2 squared. Okay, so we've got atmospheres on the top, and we've got atmospheres to the power of 1 multiplied by to the power of 2, atmospheres to the power of 3 on the bottom. So that gives us a units of atmospheres to the minus 2. Will be our units there. Right, now I think that is halfway, about halfway in the paper. So I'm going to leave that there and come back to the rest of the paper in the next video.